everybody, welcome back. We're looking at lesson 5 and today is rational functions. And what we're doing is we're wrapping up what we've learned so far on rational functions and adding one little extra tidbit and putting it all together to graphs. So this first page is really just summarizing what you've learned so far in lessons 3 and 4 on rational functions, and that's first asymptotes, vertical, horizontal, how to find them, and then also points of discontinuity, okay, which you've done in previous lessons. So we're going to take a look at the next page, and the new thing that you're learning today is when you don't have a discontinuity. So far we've looked at two types of discontinuities, and that's vertical asymptotes, which is like an infinite discontinuity, and then point discontinuities where there's like a hole in the graph. So we can actually have a rational function and have no discontinuities. And when does that happen? If the denominator of the rational function has no zeros, then there's no discontinuity. So if there's no value of x that would cause that denominator to be 0, then there would be no discontinuity. So we can just check that out. If you let x squared plus 1 equals 0 and try to solve that, look at that. You try to square root a negative number and you're no longer in the real number system. So as a result, therefore, no discontinuities. All right, so we're going to skip this investigation part and we're going to go to the next example, okay? Okay, looking at example 1, we're going to go through each of these functions that they've given you, and we're going to talk about whether they have any asymptotes, horizontal or vertical, whether they have any point discontinuities, and yeah. So first of all, because the functions are all in expanded form, so it's not factored, we're going to look at horizontal asymptotes first. And horizontal asymptotes, basically the degree of the numerator has to be equal to or less than the degree of the denominator. So just looking through here, this one would have a horizontal asymptote because it's degree 1 on top, degree 1 on the bottom. This one here, degree 2, we're okay. This one is okay, degree 1, degree 2, so the numerator degree is less than the denominator degree. Same thing here. This one, however, the degree of the numerator is 2, the degree of the denominator is 1, so this one, therefore, would have no horizontal asymptote. Okay, running through the rest, this one's okay, degree is equal, this one's okay, the degree is less in the numerator, equal, and this one would have no horizontal asymptote. Okay, and then finally on J, the degree on top is a 3, the degree at the bottom is a 2, so it's greater, so therefore, again, no horizontal asymptote. Okay, so that's how we tell if there's a horizontal asymptote. Now, to get the equation, let's go back through. It's going to be y equals, because a horizontal asymptote is obviously a horizontal line, so the equation would be y equals. And you really take the coefficient of the highest degree in the denominator, which is x to the 1, okay, and you look for that same degree term in the numerator and take the coefficient of that term, and you get 1 over 1, which is going to be 1. So our equation of the horizontal asymptote for the first one is y equals 1. Next one, x squared on the bottom, so you look for the x squared on top, and again the coefficients are both 1, so horizontal asymptote would be y equals 1. Okay, on C, degree on the bottom is x squared, the coefficient is 1, but you'll notice there's no x squared on top. So what you can do is kind of pretend there's a 0x squared, okay, which means the coefficient would be a 0. So our horizontal asymptote would be y equals 0 over 1, which is y equals 0. Okay, why don't you guys run through and do the horizontal asymptotes for all of the rest of the ones, and then we'll check back and see if we have the same answer, okay? Pause your video, please. Okay, check it and make sure you have the same answer that I do. One thing I want to point out, if you write the equation for the horizontal asymptote and you don't put y equals, you will not get the marks for that. It has to be an equation of a line, so it has to have y equals, just like vertical asymptotes have to be x equals. Okay, so now what we're going to look at, we're going to take a look at any discontinuities for x. Okay, so what we'd be looking at there is any values that would cause the denominator to equal 0. So we're really setting the denominator equal to 0. And sometimes probably the best way to look at that would be to factor if we can. So if we just look at the first one here, it's going to be x minus 4 over x plus 4, and there's really no factoring to do. So you'd let the denominator, x plus 4, equals 0, and you'd get x equals negative 4. Now because that factor, x plus 4, did not cancel with any factor in the numerator, that therefore would be a vertical asymptote, because that value of x would cause us to divide by 0, and therefore that shows up as a vertical asymptote since the factor didn't cancel. Okay, let's look at the next one. The next one, let's see, what can we factor? We could factor the numerator, but because we can't factor the denominator, I'm not sure there's much point. We could factor the numerator, but the denominator, x squared plus 4, is not a difference of squares, so there's no factoring that. As a result, x squared plus 4, there's no value for x that we could put in there that would cause that to be 0, right? Because if we square x and then add 4, we'd never equal 0. So as a result, there are no vertical asymptotes and no point of discontinuity. Oh, and this one would have no point of discontinuity. Okay, now third one. Okay, it looks like we can factor the denominator. That's good. And the numerator is x plus 4. Denominator, factor the difference of squares, x minus 2x plus 2. And do any factors cancel? No, they don't. So therefore, our vertical asymptotes are going to be when we set each of those factors equal to 0. So x equals 2 and x equals negative 2 would be our vertical asymptotes. No factors canceled, so therefore no points of discontinuity. Good. All right, let's look at the next one. Okay, so numerator x plus 2, denominator we factor, x minus 2x plus 2. Oh, and what do you notice there? We have a common factor of x plus 2. So because that canceled off, that would mean that our only vertical asymptote would be the remaining factor of x equals 2. But we would have a point of discontinuity at whatever caused this factor that canceled to equal 0. So x equals negative 2 would be our x-coordinate of the point of discontinuity. How do we find our y? We plug that negative 2 back into our simplified function, which would be, I'll just write it up here, well, the x plus 2 on top canceled, so then we'd have 1 over x minus 2. If we put negative 2 in for x, we would have 1 over negative 2 minus 2, which is equal to negative 1/4. And there we go. That's our point of discontinuity. Okay, let's look at the next one. X squared plus 4 over x plus 4, really no factoring to do. So there's no points of discontinuity because no factors canceled. Vertical asymptote, anything that causes the denominator to be 0, yep, we have x equals negative 4. And there we go. All right, why don't you guys try the last 5 here, run through, look at the vertical asymptotes, point of discontinuities, factor the denominator and numerator when you can, okay? So pause your video and work on those ones. Okay, how did those questions go? All right, so for F, we would have vertical asymptotes of 2 and negative 2, x equals, and no points of discontinuities. G, we have no vertical asymptotes or points of discontinuities because there's no value that would cause the denominator to be 0. H, we have, once you factor it, factor out the negative first, which leaves a difference of squares of x minus 2x plus 2. And that means none of those factors canceled, so we only have vertical asymptotes of x equals 2 and x equals negative 2. No points of discontinuity. Okay, I and j get a little more interesting. If we factor the numerator, we get x minus 2x plus 2, which cancels with one of the factors in the denominator. But that factor in the denominator gives us a point of discontinuity, so x equals negative 2. Okay, there's our x-coordinate of the point of discontinuity. To get the y value, you would sub back into the simplified, after you get rid of the common factor, the simplified form. So negative 2 minus 2 is going to be negative 4, and there's the coordinates of the point of discontinuity. There would be no vertical asymptotes because the only factor we had in the denominator canceled off, giving us the point discontinuity. And there we go. On J, we factor fully. We take an x squared out of the numerator, leaving x squared and x minus 4. In the denominator, we factor a greatest common factor of x, and that would become x and x minus 2. But we have a common factor of x that we can divide, but that common factor that divided right here would actually give you a point of discontinuity with a coordinate of 0, right? Because you set that factor to 0, x equals 0. Then take that 0 and sub into your simplified form. So 0 times 0 minus 4 over 0 minus 2, and you would basically get 0. So our point of discontinuity, 0, 0. Now, vertical asymptotes, we still have this factor in the denominator that didn't cancel, so that would be a vertical asymptote of x minus 2 equals 0, so x equals 2. All right, awesome. Hopefully you'll be okay to do the assignment now on those ones. We're going to do one more example, and then you'll be able to get to the assignment. Algebraically determine the equations of any asymptotes and the coordinates of any points of discontinuity on the graph of the function, yada yada. Okay, well, why don't we first look at horizontal asymptotes? Okay, so we should probably, to do horizontal asymptotes, expand this first. So we would have 2x squared outside negative 10x, inside negative 1x, so negative 11x, and then plus 5, all over top of x squared minus 2x minus 15. So to do horizontal asymptotes, we want to use the expanded form of this. For vertical and point discontinuities, we want to use the factored form. Okay, so horizontal asymptote, we take the degree of the denominator, the coefficient of that is a 1, and the same degree in the numerator, coefficient is 2, so our horizontal asymptote would be y equals 2 divided by 1, the coefficient's there, which equals 2. So our answer would be y equals 2. Okay, so vertical asymptotes, we're going to have to factor the denominator now. So we'll do that in a different color here. So we'll have 2x minus 1, x minus 5 on top. In the denominator, we have x minus 5 and x plus 3. Two numbers that multiply to negative 15 add to negative 2. Okay, do we have anything that cancels? Yes, we do. So this factor, x minus 5, is going to cancel. That's going to give us a point of discontinuity. So the x coordinate of that would be 5, because x minus 5 equals 0, x equals 5. Then let's cancel those off and simplify. We'd have 2x minus 1 over x plus 3. If we sub that 5 in for x, we'll get the y coordinate of our point of discontinuity. And that would be 10 minus 1, 9 over 8. And there we go. Vertical asymptote, okay, would be any factor that didn't cancel set to 0. So x plus 3 equals 0 would be x equals negative 3 for our vertical asymptote. Good. So we have a point of discontinuity at 5 and 9/8 and a vertical asymptote at x equals negative 3. Okay, so we've got all the asymptotes and points of discontinuity. They want domain and range now. Now domain, fairly straightforward. We can't equal those values, the point discontinuity and the vertical asymptote. So our domain should be x such that x can't equal 5 as well as negative 3. But it can be anything else, so x is an element of the reals. If you were to write that in interval notation, so in interval notation, that would be, goes from negative, square brackets, not right. It would go from negative infinity to negative 3, also union from negative 3 to 5, and then union from 5 to infinity. I think the other way is easier to write it on this one. Okay, now finally we want range. Now, unlike domain, where if you have those values of x, the domain can't equal them, for range, the graph can actually cross a horizontal asymptote. So it's possible to have a y value of 2, even though it approaches that at the far end. So what we're going to do is we're going to bring up the graphing calculator. We're going to put this into y1. Make sure you have brackets around your numerator, okay? Big brackets, and then around the denominator as well, and we'll take a look at the graph, okay? Pause your video, please. Okay, so we've got that graph. You'll notice that we're approaching y equals 2 at either far end, but in between we do not cross. This asymptote isn't actually here, this vertical asymptote, that's just an invisible line. So as a result, our range would be y is an element of the real, y cannot equal 2, but it's an element of the real.